Gay-Lussac's law, which is a little more interesting to apply sometimes, is a relationship between pressure and temperature. I actually should be labeling these 1, 2, 1, and 2. So again, as temperature goes up, kinetic energy goes up. So frequency of collision goes up. Gay-Lussac's law applies for a container that is not only closed, but has a fixed volume. So the volume will not change regardless of what is going on here. So if our temperature goes up, so let's say we start at 1 atm and we have a container that's at 50 Kelvin, and we want to find out, well, what will that pressure be if we were to go to 100 Kelvin? Simply, again, our cross multiply and divide. And we cancel everything out, then we'd find that we were at 2 atm. So if we have that same surface area, but it's getting hit more often, then our pressure is going to go up. So again, this is also a relationship that is directly proportional. So to think of this in terms of something that you might see every day, think of the issue with, say, having a spray can in your car. That spray can does not have a volume, since it's made of metal, that will want to expand. So if it's sitting in your car that gets hot as it's sitting out in the sun, these air particles are moving more rapidly. They're hitting the sides of the container more often, so that increases the pressure to the point where this spray can might even explode, because the force of all these little air particles hitting the surface area of the can become too much for the can to hold up against. Another weird way to think about this is sometimes if the gas in something is released very quickly, so if a gas is released quickly, then that means its pressure is decreasing rapidly. So if, again, these things being directly proportional, if pressure were to go down, temperature would go down. So then also the temperature would drop. So you might see this sometimes if you buy one of those cans of compressed gas just to clean off your computer, that if you spray it very quickly, actually what you might see is sort of some liquid condensation end up on your keyboard, because that gas was released so quickly that it became a liquid. And then finally, we can pull this all together into what is called the ideal gas law. So in the ideal gas law, we have to say what an ideal gas is. Basically, an ideal gas is a gas that is, again, all the particles in random motion. It means that there are no attractions between particles. For instance, we might think of noble gases being closest to ideal gases because they don't want to bond, they're not in molecules that are polar. Also, that they would have no mass, that they would not be affected by gravity. So right away you might think, well, why would we use this law? Because obviously there are a lot of different gases that don't fit this description. Obviously that atoms do have mass. We've seen polar and nonpolar molecules that might be attracted to each other. But most things will fit the ideal gas law. And finally, that any collisions between particles will be fully elastic, which means the kinetic energy with which two particles hit each other should completely equal the kinetic energy when those two particles, after that collision. So the ideal gas law is basically this, that the pressure and the volume will equal the number of moles, N equals the number of moles, times the gas law constant, times the temperature. So this ideal gas law constant, R, is different for depending on which units of pressure you're using. If you are using ATM, it is 0.8205 liters times ATM per moles times Kelvin. If you are using kilopascals, it is 8.3145 liters times kilopascals over moles. And then it is 62.364 liters times torr, which is also millimeters of mercury, for moles times kilograms. And if you think about the importance of moles, for instance, the more particles of a gas that you put into a container, for instance, if I were to put 1 mole of gas, I should expect into a balloon, and then I put 2 moles of gas into a balloon, I should expect to see that since I have double the amount of particles, I should have double the volume of the balloon, provided that all these other constants, pressure and volume, are held constant. So looking at some application very quickly. If I have, for instance, if I wanted to decide what would be the pressure of a gas that had a volume of 1 liter, and that was at 100 Kelvin, and if I had 1 mole of that gas, and I wanted to know what the pressure was in ATM, I would just plug my numbers in. So pressure should equal, and then we have our 1 liter. We had 1 mole. The gas constant that we would use in this case would be 0.08205 liters times ATM over moles times Kelvin, and then our temperature of 100 K. So our Kelvin cancel out, our moles will cancel out. If we move liters over here and divide, 1 liter, so liters will cancel out. We are left with 1 times 0.08205 times 100 Kelvin, which means we should have a pressure of about 8.205 ATM.